for I guess here. So for linear transformations, for a linear transformation, say T V to W, right? I guess let's see where V and W are finite dimensional. We can immediately deduce another property. And what is that property? Well, the property is onto, the idea of surjective, right? So what does surjective mean? Well, I guess let's say definition. A linear transformation T to V to W is called onto, or you can say surjective, if for every W in W there exists a V in V such that T of V is equal to W. So what does that mean? If you were to draw it in a picture, and here's V and here's W, and here's T going between both of them, everything in W is hit by T, is basically what it says. So everything that's in W is being hit by T under the image of some vector in V. So that's what onto and surjective means, right? So instead of so now why am I defining this? Well, because the idea of this onto, you can see the definition is kind of like weird. Like for any W there exists a V, and like who's gonna want to check all that, right? Well, as long as V and W are finite dimensional, one-to-one immediately implies onto. So as soon as you have one-to-one, you don't even have to check if it's onto, it's immediately onto. So that's a result that we have here. So here, I guess, let me see what the last theorem was. 6.4. If T is a linear transformation between two vector spaces V and W, where both are of dimension wait, hold on. Wait, I don't think this is. I don't think they're phrasing it right here. So we can make it more general. Are of finite dimension, then T is onto or one-to-one if and only if it is onto. So as long as you have two V and W be finite dimensional, one-to-one implies onto. Okay. Now you can from there you can say if they're both of the same size, then they're bijective, right? I mean, meaning it's a one-to-one correspondence, I guess you'd say. But so before I talk about that, maybe I should mention mention a few words about, I guess maybe do a few examples. Or maybe I don't think the example, I don't, because I'm not gonna ask you to do all that. What I'm gonna ask is the stuff from that next section, basically. Okay. The next idea, okay, so the next idea is basically what I said bijective, right? But what does bijective mean? Well, what I mean by that is something called isomorphisms. So now we have built an idea for comparing sizes of vector spaces. I think the 7th of May is the final, using onto and one-to-one. Right? So what the whole point of this was because I'm trying to compare what the size of a vector space V is in comparison to a vector space W. So let me ask you this. If you know, like for example, if I have a set here, right, with like things in here, and I had another set here with a bunch of other things here, and I had a, let's say A and B, and I had a function going between them, and I told you the function is one-to-one. What can you immediately tell me about the size of B in comparison with A? Is it less than it? Is it greater than it? Is it equal to it? Or what? Not equal, but close. It can be less than or equal to it, right? Because remember, one-to-one means that each one gets mapped to a single one over here. So I know there's at least that many vectors in B that's in A, right? Because each one is just getting mapped. It could be less because I mean there could be vectors out here that didn't even hit, right? So it can be less than or equal to it. Now, adding the idea of onto, meaning that the entire set, remember, the idea of onto means that W was completely hit, right? If I can guarantee that not only is it onto, but the entire set is hit, then what can I say about A and B? The size. They're the same now, right? Because if all of B here is being hit by everything in A, and it's one-to-one, meaning only one is getting mapped to one, so it's like you're literally like counting the elements in B with A. And if it's onto, meaning you hit every single element in B, they have to be of the same size. So you see now kind of like how this idea is being developed here. Onto and one-to-one gives me a way to compare sizes. Now, this is for sets. You can compare the size of it, but given that these things are vector spaces, isomorphisms, it not only does it tell you that they're the same size, but it can tell you a lot more things as well. So the next thing is this. What is an isomorphism? So, or I guess even better, sometimes two vector spaces may look completely different, but may act the same with with their given structure. What do I mean by the given structure? I mean the addition and multiplication that's on each vector space. So basically, this is like the idea, if this vector space, I give you two vector spaces. The elements in the vector spaces are completely different. One could be polynomials and one could be like the arrow stuff, right? Okay, but if I observe them a little bit closely, I see that here, this space here, if like I see how they behave, and then when I go over here and I see how they behave, and they're behaving very similar. Like there's like almost no distinction. The only distinction is that these are like functions and these are like arrows. Well, for us, as long as they behave the same under the structure, they're basically the same. They're not equal, but for all the I guess for us it'd be good enough that they're the same. So that's the idea of isomorphism. They're not equal, but they're similar enough that we're going to consider them equal. Okay, so that's what isomorphism is. The reason I'm saying that is because the definition of isomorphism is kind of weird. It almost gives you no meaning to it, but that's the meaning of it. So a linear transformation T from B to W is called a isomorphism if it is onto and one-to-one. Okay, so again, the definition is kind of like kind of wonky, but basically what it's saying is that in this case, I guess so you can say in this case we also say that V and W are isomorphic, and we denote it like this. Okay. Again, what this is telling you is basically V and W, while not the same thing, act closely enough like each other that we're going to consider them the same thing. So they're not equal, but they're basically the same vector space for all intents and purposes. Okay, so okay. So now we have this idea of isomorphisms. Okay. Now here is the punchline, I guess. The entire time in this entire section so far, we've been talking about linear transformations, right? And I've always been telling you, all linear transformations are not matrices, right? But all matrices are linear transformations, and it's true. Not all of them are. But if V and W are of finite dimensions, right? Then we can always just represent T as a matrix. So even if it doesn't look like a matrix, there's as long as V and W are finite dimensional, there's a matrix representation of T out there, and that's basically what this is. This entire thing led to. It's basically so. This results in the following theorem. Theorem 6.1.5. If V and let's say if V is of finite dimension, then there exists a n in n such that V is isomorphic to a copy of Rn. So basically, any finite dimension, what this is basically telling me is, no matter what the vector space is, as long as it's finite dimensions, it behaves exactly like Rn. So like those arrow things that you always are working with, you can just consider everything there as an arrow, basically. And that is made rigorous by this. So this gives us a way to represent matrices, or sorry, linear transformations between finite dimensional vector spaces as matrices. Okay, and this will lead into section 6.20 basically. Okay, any questions so far? Okay, well, now we're in section, I guess, 6. Oh, was I already in 6.2? That was, so what was I putting? Whatever, I'll change the numbers, doesn't matter. Section 6.3. Matrix representations of linear transformations. Okay, all right. So, question: how do you represent a matrix or a linear transformation as a matrix? And the answer is basically this. As long as you know what occurs to the basis elements of the vector space, if you know where they go under the transformation, then you know where every other vector goes. As soon as you know where those basis elements go, every other vector is determined by where those go. Which basically means this. If I take T, the linear transformation, and it's not like in a matrix form, and I apply the transformation T on each basis element, it's gonna give me some vector thing, right? But basically what you do after that is basically whatever you get, what it spits out, you make a matrix with those things being the columns. So here's what this is. Well, I guess maybe I should mention first, like this. The answer is okay, so the matrix, I guess I'm gonna say, the matrix is determined by where the basis elements of V go under T. Okay, so for example, let's make a theorem for right now. So theorem, let's say 6.31. For right now, let's just suppose that we have a linear transformation. So let T be a linear transformation from Rn to Rn, right? And let and B be E1 all the way to En, be the standard basis of Rn. Okay. So let me make this a bit smaller so I can finish writing. Then the matrix representation of T is A. Well, like I said, you take A and you construct it like this. You take T of E1 and put that in the first column, and then you continue this pattern until you put E of N in the last column. Okay. So this is what the matrix is basically going to be. You take T, apply it on the basis element, and then boom, it goes, and there you go. There's the matrix. Yeah. So let's see. All right. So let's look at an example then. Let's see. Example. Let's say T from R3 to R2 be defined as T of X, Y, and Z be equal to the vector X minus 2Y, 2X plus 2Y. Okay. Find the matrix representation. All right. So according to that theorem I just stated, what do you think you guys will do to find the matrix that does what T does? So what is the standard basis in R3? Would it be something? So what is E1, E2, E3? So here E1 is equal to 1, 0, 0, right? E2 is equal to 0, 1, 0. Oh yeah, by the way, I forgot to mention this. So I've noticed that a lot of you have not done as much homework as I hoped. Maybe, I don't know, maybe I probably made the homework too hard. But basically what I'm gonna do is I'm gonna do this. I'm basically gonna hold homework sessions solving some of them, a lot of them that you guys haven't solved. That way you guys at least have done some of it and not like, you know, at least that way I don't just take this anything. So I have to organize when those sessions will be, but I do because yeah, I saw that many of you have done much of the homework. But anyway, that's I'll mention more about that later. Okay, anyway, so this is the basis elements for R3, right? Yeah, because like I said, I saw that many of you have not done as much homework as and it's almost the end of the semester. there's like maybe like 3 of you or 4 of you who have done basically what you're supposed to have been done. Well, at least at this point. But yeah, I'll do homework sessions. I just have to go and look at the problems, the most problems that people have not done, and do those with you all. Oh, okay. Well, okay. Well, then that's probably a good. Yeah. I honestly didn't think it was gonna be that bad, but I'm gonna go through all the really. I'm basically gonna set aside maybe. I say maybe 5 to 6 days, sometime, and do those homework problems. We're gonna do a week 10. I think is by what we should have done by now. But yeah, but don't worry. Like I said, I saw that. Yeah, week. Oh, sorry. Yeah, week 10. So yeah, so I'm gonna do the homework with you guys because yeah. So I don't want to just leave you guys, I guess, in the hanging with all that. So yeah, we'll definitely do that. Right now, what time is it? So May 7th is the final. So I expect maybe sometime during the week or on the weekend, and I'll record those sessions for the people who can't do it because I'll be in my apartment with my computer so I can like download it there. So yeah, we'll do some for that for sure, and I will definitely do some of the homeworks because, like I said, I did see that and I was like, oh, maybe I should have maybe not given all those homework problems out. But okay, but it's fine. Anyway, continuing with this. So how do we find the matrix A from here? So literally all you do is this. What's T of E1? Well, T of E1 is going to equal what? Well, it's going to be 1, 0, 0. So it's just going to be 1 and 2, right? What's T of E2? Well, T of E2 is going to be 0, 1, 0, which is just going to be minus 2 and 2. T of E3, well, that's just going to be 0, 0 here. Yeah. All right. So all you have to do at this point is literally just do what I said in the theorem. And so A is going to equal this. So literally just plug in. Okay, so the first one is 1, 2. Second one is minus 2, 2. And third one is 0, 0. And that's it. So now basically what this is this transformation here, instead of having to do this, all that information is captured by that matrix. So for example, if I wanted to know what T of 3, 3, 3 was, instead of me plugging it into T, just multiply by this matrix and it'll give you the same answer. Oh, and also if, for example, you wanted to find the kernel, right, of T, instead of finding the kernel of T, you can find the null space of A, and you know how to do that, right? Also the same, if you want to find the image of T, instead of doing that, just find the column space of A, and so on and so forth. Like everything that is being, I guess, embodied by A translates to T is basically what has happened here, right? So that theorem basically created a bridge between matrices and some like weird thing called linear transformations. So now we can like go between these bridges. So if you don't understand something here that's in linear transformation land, just cross a bridge to matrix land, do your stuff there, and then come back, kind of thing. Okay. All right. All right. So let's see another So now we have something else. So much like functions, we also have a idea of composition
This memory began when Dad booked his family's summer vacation.
of linear transformations.
Book early, cancel if you need to.
So remember in college algebra, you were like doing this, like for whatever reason, when I was, I always call this fog, but it's the composition between F and G, right? So much like how you have this in just college algebra, you have the same thing between two linear transformations as well. So definition. Let T1 we go from B1, no, let's say B to W, and T2 be from W to Z. Be linear transformations. Linear transformations. Then decomposition between T1 and T2 is defined as follows. So, I mean, define it. So if you do, okay, so T1 goes there. Okay, so T2 composed with T1 at a vector V is just simply going to be T2 evaluated at T1 of V. Okay, so this is called the composition, okay, of two linear transformations. Okay, but maybe you guys don't like compositions as much as the other person. So what do we remember? We built this bridge already, right? So why not do it with matrices now? So again, we can do this with matrices. And how do you do it? Basically, exactly what I was thinking. So 6.32. So let T1 from B to W and T2 from W to V or Z be linear transformations. Okay. Oh, and oh yeah, and then and A1 and A2 be their matrix representations. Then T2 composed with T1 can be written as the following. Okay, so basically this multiple matrices. Oh, or I guess even better. Then T the better. Then the matrix representation of T2 close with T1 is, okay, so you're gonna go from, okay, so hold on, so you can go from A, B2, okay, so it's gonna be just A1 times A2, basically, right? It's just literally just, you just multiply these matrices instead. So instead of one, so basically what it's saying is instead of doing the composition like how I wrote it in the first definition, just find the matrix representations for T1 and T2 and then multiply them together, and that's the same thing as if I were to compose T1 and T2. So example. So for, let's say, T1 of, I don't know, say x, y, z is equal to, let's say, 2x plus y, 0, x plus z. And T2 is, of x, y, z is equal to x minus y, z, and y. Right? Find T2 composed with T1 matrix representation. Okay, solution. Well, first we're gonna take, well, by the way, what is this linear transformation between? The first one is from R3 to R3, right? The second one is from R3 to R3. So we're gonna do T1 of E1, which is gonna give me what? So 1, 0, 0 will give me 2, 0, 1. T2 is E2. Oh, sorry, not T2. We're still on T1. So plug in 0, 1, 0. 1, 0, 0. And then T1 of E3 is equal to, okay, 0, 0, 1. And then T2 of E1 is going to equal, okay, so T2 E1 is 1, 0, 0, so it's just T2 of E2 is going to be 0, 1, 0, plus minus 1, 0, 1, 0, 1, right? So T2 of E3. By the way, if you guys have no idea where I'm taking it from, it's literally this example, right? I'm just doing those vectors. 0, 0, 1. So 0, 0, 1. Right, so A1 is going to equal 2, 0, 1, 1, 0, 0, 0, 0, 1. And A2 is going to equal 1, 0, 0, minus 1, 0, 1, 0, 0, 1. And so from there, just multiply A2 with A1, and that's the wouldn't T2 of E3 be 0, possibly, maybe, yeah, you're right. Yeah, there we go. Perfect. Okay, so now just multiply A1 and A2 and you get decomposition. So, I mean, you know how to do. Yeah, it'll be all day. I'm just gonna remove the whatever specified time and just say it's an all-day exam. Take home as well. Yeah. Okay. So this is how you do that. All right. So yeah. All right. Now let's skip that part. I don't think it's pertinent to what we need to do. Yeah, we're not going to do that. I mean, that's just it's just basically if I mean yeah, it was an assignment for me. Basically, the next thing I was going to say is okay. So just as I mean, so what does it mean for a linear transformation to be invertible? Well, it literally just means that there exists another matrix. I guess I should just define it and then we won't worry about it afterwards. But so definition, we say T from V to W is invertible if there exists a, let's say, another linear transformation, say S from V, or sorry, oh sorry, I think it has to be between the same vector space. Yeah, it has to be. Such that T composed with S is equal to S composed with T is equal to just the identity map, basically. So basically, when you compose them together, it just becomes the identity, basically. Remember, what does the identity mean? It means that if I evaluate a vector on it, it just gives me that same vector, just like how the identity matrix gives me that same thing. But I mean, you can just do that with its matrix representation. Now, you might have noticed something a little not odd, but like the entire time I was just doing these matrix representations in Rn, right? All of them were just we were just spitting out vectors. I mean, everything was in Rn or Rn, like R3, R4, or R5. So what happens if I want to do a matrix representation on the vector space of polynomials or to Rn, or the vector space of polynomials to the matrix, the space of matrices? So how do I even do like a matrix representation there? Well, what you have to do is then you have to create a change of basis. So you have to change so for example, if the basis for the space of polynomials was 1x and x squared for the space of polynomials of degree 2 or less, how do I get a matrix representation out of that? If the linear transformation was a derivative operator, well, we'll see, and we'll see. Don't worry. If this is like just like bouncing off of you, you'll see examples. But basically, the idea is this: we're gonna change the coordinates of the polynomials to the coordinates in Rn, and we're gonna do that So this is where I'm gonna come back to the change of basis thing. So I guess before we move on, I have to talk about a little bit of change of basis. So for the next 4 minutes, I'm just going to talk about that briefly. So suppose that we have two vector spaces. B and W with basis B is equal to, like I say, V1 all the way to Vn, and okay, so let's start off with um, okay, so here, let's put it right there. Right, with a basis of V. Let, I guess, a W be in W. Then the coordinates of W with respect to, I say, B is denoted as, I guess, W, and then you put this bracket with B here. So that just means that this is the coordinates of W with respect to the basis B. And how do you find that? Well, is the vector, or the vector C1 through Cn, where W is equal to C1 B1 plus all the way to Cn Vn. Okay, so as if you write W as a linear combination as the basis elements in V, those constants that are in the front are your coordinates for W. So basically, it ends up being this right here. So basically, we say that W bracket in B is equal to C1 all the way to Cn. Okay, and this is what's going to give us the idea of how to make a matrix representation out of different vector spaces that isn't just Rn. Yeah. Okay, so I guess maybe we should do. Well, it's time. So next time we'll do an example of change of coordinates. So I'm going to actually give a concrete example here. So vector, let's find the coordinates of this vector with respect to a non-standard basis, and you'll see basically how you do it and all that. And basically after that, then I'll show you how to do matrix representations in different vector spaces like polynomials, and then that would finish the section off. And the next section would be transition matrices. So that one's going to be a little harder because you're going to have your first commutative diagram there. And then after that, that should finish what I want to talk about, linear transformations, and then when we go to eigenvalues and eigenvectors. Okay, so yeah, so in regards to the homework, I will send out an email, and I'll try to basically set up a time that will basically as many people who come, but I'll record it as well. And so I can do as many homework problems with you guys as possible. So I'll probably start off with the harder stuff, so like the vector space stuff, linear inner product spaces, and all the other stuff that's probably a little bit harder. Do all those. Well, not all of them. I'll pick out the hard ones, and then we'll go back to the first week's stuff. But yeah, so we'll do that, so at least you guys can like get some of the homework done that way. All right, that's it.